Sorry, I forgot to start record, so I'm going to go back to the first example and just show that on the video. Okay, so here we have dp dt equals p times 4 minus pp minus 8. Letter A, dp dt is equal to 0, meaning it stays at 0 if p equals 0, p equals 4, and p equals 8. Those are all of our equilibria. Letter B, using a phase plot, determine which equilibria are stable and which are unstable. And so for that, a phase plot is a graph of p prime versus p. It's a cubic whose leading term is negative, so it starts negative, and then at 8 it goes positive, at 4 it goes back to negative, and 0 goes back to positive. Now where the graph is positive, it points to the positive direction. Where it's negative, it points to the negative direction. Where it's positive, it points to the positive direction. Where it's negative, it points to the negative direction. And so the equilibria, p equals 0, p equals 4, and p equals 8, at p equals 0, they point towards each other. So that's the lines pointing to each other is called the phase line. And so that's stable. P equals 4 is unstable because they go away from that point. And p equals 8 is stable because they both are facing to that point. Using the phase line, graph the stable equilibria. So we have 0 tangent lines down at p equals 0. P equals 4, we have 0 tangent line, and 8, we have 0 tangent line. Our graph, we can see that below p equal to 0, we have positive tangent lines. Above, we have negative tangent lines. Above 4 but below 8, we have positive tangent lines. And above that, we have negative tangent lines. So if we started off at 3,000, then we see that the graph is going to tend towards p equals 0. For 5,000, we see that this graph is going to tend towards the population of 8,000. And if you pack too many people in there, 10,000 people, it's going to go back to 8. So we say that if p naught is 3,000, the limit as t approaches infinity of p of t, 3,000 goes to 0. If p naught is 5,000, then the limit as t goes to infinity of p of t is 8,000. And if p naught is 10,000, then the limit as t approaches infinity of p of t is also 8,000. We did a lot of existence and uniqueness theorems in this class. This is going to be important on the final. So existence unique, or sorry, state whether the differential equation is linear or nonlinear. Because we're multiplying, because we have a y times a dy dx, that makes this nonlinear. Dy dx is the natural log of x minus 2 divided by y minus 5. We see that f of x comma y is discontinuous at y equal to 5 and x equals 2. And we want to know the conditions for existence of a unique solution, or the largest open interval, or rectangle in the case of a linear. We're looking for a rectangle that contains the point 1 comma 5 where f of xy is continuous. But since f of xy is discontinuous at y equal to 5, there is no rectangle containing 1, 5 where f of xy is continuous. So the existence uniqueness theorem doesn't hold here. We can't guarantee existence uniqueness because of that. Now this problem, linear versus nonlinear, means linear in the y and the y prime. There's no exponents on our y's. We're not multiplying any y's. Doesn't matter what you do to the t's. And so this is linear. When you have a linear equation, we write it in the standard form by dividing by t squared minus 9. Okay, so now we're looking at where 1 over t squared minus 9 and tan t over t squared minus 9, we look at where they are discontinuous for t. And so we see that we have discontinuities for t equal plus or minus 3. And tangent is undefined at pi over 2, 3 pi over 2, and so on. So we're looking for the largest interval containing the point x not equal to 2, where these both are continuous. So we see that -3 +3 and pi over 2, which is around 1.57. The point x not equal to 2 lies in here from pi over 2 to 3. So that's the largest interval containing the point x not equal 2, where both those functions are continuous, is pi over 2 to 3. So largest interval for existence and uniqueness is pi over 2 to 3. All right, so the first order nonlinear ones, you had to set dy dx equal to f of x comma y and look at for the largest rectangle containing the point where the function's continuous. And the linear one, you just look for the interval that contains the point for which the functions are continuous. Solve the given initial value problem. We did these by integrating factors. We divide by t cubed, y prime plus 4t squared over t cubed is 4 over t, y equals t to the negative 3 e to the negative t. Our integrating factor mu is e to the integral of 4 over t dt. Integral of 4 over t is 4 natural log of t. We don't need constants of integration when we do integrating factors. 4 goes up top, and we have e to the natural log of t to the fourth, which is just t to the fourth. So now we multiply the left side by t to the fourth. And t to the fourth times t to the negative 3 is t. Okay, so remember when we do integrating factors, when you multiply both sides by the integrating factor, this is always the derivative of mu times y. So this is the derivative of t to the fourth times y, and that equals t e to the negative t. So we integrate both sides now and get t to the fourth times y equals the integral of t to the negative t times dt. We integrate that one by parts. U equals t, dv equals e to the negative t. du equals dt. And v equals negative e to the negative t. So this is negative t e to the negative t minus the integral of v du. It's a plus e to the negative t dt. Integrating e to the negative t as a minus e to the negative t. This is where we will add a constant. We divide by t to the fourth, and we get y equals negative 1 over t cubed e to the negative t minus 1 over t to the fourth e to the negative t plus c1 over t to the fourth. We know that y of negative 1 is 1. Y of negative 1 is negative 1 over negative 1, which is 1, e to the first. This is minus 1 over positive 1 e to the first plus c1 over 1, and we know that y of negative 1 is 1. And so that's equal to 1, or that says that our constant of integration is 1, and therefore we have y of t is negative 1 over t e to the negative t minus 1 over t to the fourth e to the negative t, and then this is plus 1 over t to the fourth. All right, integrating factors definitely on the test. Give you something a little easier than that one, though. Okay, so I need to remind you that this was a linear dE. It had a non-homogeneous term, and it had variable coefficients. They weren't constants. This one is a nonlinear differential equation because the y minus 1 is to the 2/3. So we can't use integrating factors on something like this. So we're kind of stuck with separating our variables. So we divide by y minus 1 to the 2/3 and get negative 2/3 dy dx equals 6x, or y minus 1 to the negative 2/3 times dy equals 6x dx. So now we integrate both sides of this, and when I integrate y to the negative 2/3, I add 1, which gives me 1/3, divide by 1/3, which is 3 times, and then integrating x is x squared over 2, or 3x squared, and I'll put a constant of integration in there. Now it's just a formal process of solving for y. We have y minus 1 to the 1/3 equals x squared plus c1 over 3, which is some new constant c. And now we just cube both sides and then add 1. All right, separating variables is also important. Number 6, verify that the differential equation is exact and then solve the equation. So remember, our total differential takes on the form of fx dx plus fy dy equals 0. And then this comes from having some kind of equipotential function f of xy equals a constant. That means the differential is 0. And so we're wondering if this m dx n dy is such that the left side represents a total differential. So if this really is some fx and this really is some fy, then we know that the mixed partials will be equal. So we check the mixed partials with it, which is fxy and fyx. So we check if my is equal to nx. So this is the check if it's exact or not. And if this is m, then my is 6x minus 3y squared. And nx is 6x minus 3y squared. Therefore, we have an exact differential equation. So now that we know it's exact, we know that that m really is the fx. Since we know fx is 6xy minus y cubed, then we know f is the integral of that with respect to x, which gives us 3x squared y minus xy cubed. Y's are all constant. But we need to have a constant of integration there. When we integrated with respect to x, we assumed all y's were constant, so we have some kind of function that's constant, which could be up to y's. Now we know this is fy, so then the g of y will tell us what we're missing. So to compare it with fy up there, 4y plus 3x squared minus 3xy squared, we differentiate this with respect to y, which gives us 3x squared minus 3xy squared plus g prime of y. Now this is supposed to be equal to 4y plus 3x squared minus 3xy squared. And so we see that we have the 3x squareds, the negative 3xy squared, so we see that g prime of y is 4y. If g prime of y is 4y, then g of y is y squared times 2. So now we've recovered our f of xy. It's 3x squared y minus xy cubed plus g of y, which is plus 2y squared. Okay, so we had a section on finding integrating factors for these. It won't be on there, but I will ask you on the final. I will give you the integrating factor and have you multiply both sides by the integrating factor and then show that's exact and solve that. So you will see something like this on the final. Homogeneous. This one is homogeneous because dy dx is 4x squared over 2xy, which is 2x over y, plus 3/2 y over x. And so we see that it's a function of y over x. Or you can set x equal to some constant times x and y some constant times y. And if those constants cancel out and you get the same thing, 2 times kx over ky plus 3/2 ky over kx. If those k's cancel out and nothing's changed, that's what we call homogeneous. Okay, so therefore this is homogeneous. And when we have a homogeneous differential equation, we make the shift or change of variables and we let v equal y over x. So that what we'll have is 2 over v plus 3/2 v. But the problem is if v is y over x, then y is equal to vx, and dy dx equals dv dx times x, dx dx times v. So that's what we have over here. Now v prime x plus v equals 2 over v plus 3/2 v. All right, now we should have a separable differential equation. This gives us 4 plus 3v squared over 2v we have v prime x equals 4 plus 3v squared over 2v minus v. Where that's 2v squared over 2v. And so we have v squared plus 4 over 2v. All right, that's our separable differential equation now. We have dv equals dx over x, and this is 2v over v squared plus 4. When we integrate both sides, if you let u equal v squared plus 4, then du is 2v. So that's the integral of 1 over u, which is the natural log of u, which happens to be v squared plus 4. V squared plus 4 is always positive, so no absolute values are necessary. And now the integral of 1 over x is the natural log of absolute value of x plus some constant. We take e to both sides. And that gives us v squared plus 4 equals e to the c1 is some new constant times x. V squared equals cx minus 4, and v is y over x. So that's y squared over x squared, or y squared equals cx cubed minus 4x squared, and y now is plus or minus the square root of cx cubed minus 4x squared. Okay, so we have these mixture problems. Initial value problem. So the initial value problem is going to say y prime equals the rate in minus the rate out. The rate at which the substance is going in minus the rate at which the substance is going out. Y represents the amount of salt in the container at time t. The amount of salt in the container. So if the y is the amount of salt in the container, then y prime is pounds per minute, how it's changing. And so the rate in says that water containing a quarter pound of salt per gallon is poured into the tank at a rate of 4 gallons per minute. And it has 1 pound of salt, 1/4 pound salt per gallon. The gallons cancel and we have pounds per minute, so that's 1 pound per minute that the salt is coming in the tank. The rate out leaves at the same rate, 4 gallons per minute. But the water leaving the tank is variable. So we need to multiply by some kind of pound per gallon. And we know that Y of T is the amount of pounds of salt. And so the concentration then is Y pounds of salt for 120 gallons of substance in the tank. 4 goes into 120 30 times. And so now we have rate in minus rate out. If it says write the initial value problem, now you have to tell me how much salt is in the tank at time 0. Fresh water. Okay, so this is a simple linear equation with constant coefficients. And so our mu is e to the integral of 1 over 30 dt, or e to the t over 30. So we multiply both sides by e to the t over 30. And the left side is the derivative of e to the t over 30 times y. We integrate both sides. This is going to give us 30 e to the t over 30 plus c multiply both sides by e to the negative t over 30, and we get 30 plus c e to the negative t over 30. And now we know that y of 0 needs to be 0. So y of 0 is 0, so that's 30 plus c must be 0, or c is negative 30. Y of t is 30 minus 30 e to the negative t over 30. So after a very long time, the limit as t approaches infinity of 30 minus 30 e to the negative t over 30 is equal to 30, because the limit as t approaches infinity of e to the negative t over 30 equals 0. Another way to explain our reasoning is that if you're putting in water containing a quarter pound of salt per gallon after a very long time, that's what it's going to have in there, quarter pound of salt per gallon. And if there's 120 gallons, 1/4 of 120 is 30. You can always find the limiting amount just by looking at the information. When will the tank contain half of the limiting amount? Well, that's going to be fine t, so that we have half of the limiting amount. 15 equals 30. Looking at the wrong one. 30 minus 30. E to the negative t over 30. 15 minus 30 is negative 15. Negative 15 over negative 30 is 1/2. Take the natural log of both sides. T is equal to negative 30 times ln of 1/2, or 30 times ln of 2. All right, that's when the tank contains half the limiting amount. Next problem says, suppose that we stop this process right after the tank contains half of the limiting amount and start pouring in fresh water. Then now the rate in is 0 because we're putting in fresh water. No salt is entering anymore. And the rate out, it's still going out at a rate of 4 gallons per minute. And we still have y of t measured and over 120. So then we still have the y over 30. So the differential equation is y prime equals negative 1 over 30 y. So only the salt is leaving the tank. And then it's initial value problem. So the initial value of salt that we have in this container, remember we let it go down to half of the limiting amount, or 30. So y of 0 is 30. All right, Newton's law of cooling says the rate of change of the temperature of a hot T prime is proportional to the medium's temperature surrounding medium and the temperature of the coffee. And so the surrounding medium is 60 degrees Fahrenheit because that's the room temperature. (60 minus T). Okay, so that's a linear equation with constant coefficients. We have T prime plus KT equals 60 times K. The integrating factor mu is e to the KT. So we have e to the KT on the left times T, derivative of that. We multiplied 60K by e to the KT. Now we integrate. Left side is e to the KT times T. E to the KT divided by K gives us 60 e to the KT plus some kind of constant C. So we see the temperature of the cup of coffee is 60 plus CE to the negative KT. Our initial temperature, set up the differential equation with the initial value. I was supposed to do that from the start. The initial temperature is 200. If that's the case, then 200 equals 60 plus C, or C equals negative 140. (60 minus plus 140). Okay, now we just have to find K. And so that's found by knowing that after 6 minutes, we're at a temperature of 170. So we got 170 equals 60 plus 140 e to the negative 6K. 70 minus 60 is 110 over 140 equals e to the negative 6K. K equals natural log of 11/14 negative 1/6. Will we write that as the natural log of 11/14 raised to the negative 1/6? There's k. So we put that back in there. T of t is 60 plus 140 e to the negative kt. What that gives us is the natural log of 11/14 t over 6. All right, so when you put e to the negative kt, we have e to the natural log of 11/14 t over 6, which gives us 60 plus 140 times 11/14 t over 6. When will the temperature reach 130 degrees? (130 minus 60 is 70 over 140 is 1/2 equals 11/14 t over 6. Take the natural log of both sides. Gives us the natural log of 1/2 equals t over 6, the natural log of 11/14. It says t is 6 times the natural log of 1/2 divided by the natural log of 11/14. Number 10, an object of mass 10 kilograms is released from rest 900 meters above ground and allowed to fall under the influence of gravity. So we have this object that we've released, and it has its weight due to gravity pulling it down, and then we also have a force due to air resistance proportional to the velocity. I'm going to take downward to be positive, which means this position is going to be x equals 0, and down on the ground is going to be 900 meters. Okay, so we know that some of the forces on the object is equal to its mass times acceleration. So its mass times acceleration, it's got an mg in the positive direction and a minus bv in the negative direction. So the acceleration is equal to g minus b over mv. And we know that this is dv dt. We know that v of 0 is 0. All right, so this is a linear equation with constant coefficients. We got plus b over mv equals g. We get an integrating factor, which is e to the b over m t times v. We multiply both sides by e to the b over m. We integrate both sides. And this gives us mg over b, e to the b over mt plus c. V of t is mg over b plus c e to the negative b over mt. But we know that the initial velocity is 0. So that's going to tell us then that c must be negative mg over b. Okay, there's the velocity. Now if we want to know when the object strikes the ground, we'll need to know what the height is at any given time. So x of t is equal to mg over b times t. We integrate this, and this gives us a positive m squared g over b squared, e to the negative b over mt, plus another constant. And we set x of 0 to be 0, which tells us that c is going to be negative m squared g over b squared. All right, so our height is x of t is mg over bt plus m squared g over b squared e to the negative b over mt minus m squared g over b squared. Okay, object strikes the ground if x equals 900, but the problem is we have this equation in here with the negative b over mt with the t in there, so it's a nonlinear, it's hard to solve. So we say it's going to take a while to hit the ground, so if t is really large, then we assume e to the negative b over mt has gone to 0. So we say that mg over bt minus m squared g over b squared equals 900. And solving for t there, we have 900 plus m squared g over b squared times b over mg. And we said that the mass was 10 kilograms. We said that b was equal to 10. 10 and 10, so this is 1 over g times 900 plus m squared over b squared, so this is plus g 900 over g plus 1. Exam 2. This is where we started looking at second order constant coefficients, and we would use the characteristic equation on these to solve. And so it was always a y double prime plus by prime plus cy equals 0. And the characteristic equation was always ar squared plus br plus c equals 0. And we would find that by setting y equal to e to the rt. So letter A, I want to go back to s's now because we just did Laplace transforms. We have r squared plus 16, that y prime is r, equals 0. So there's our characteristic equation. That's r times r plus 16 equals 0, or r equals 0 and r equals negative 16. So our general solution is C1 e to the 0t plus c2 e to the negative 16t, which is c1 plus c2 e to the negative 16t. Y of 0 is negative 1 says c1 plus c2 is negative 1. And y prime of 0 equals 1. That c1, when I differentiate it, it goes to 0. So we have negative 16c2 equals 1, or c2 is negative 1/16. Then that says that c1 is negative 1 minus c2, or negative 1 plus 1/16, which is negative 15/16. All right, so then y of t is negative 15/16 minus 1/16 e to the negative 16t. Here the characteristic equations r squared plus 4r plus 8 equals 0. And so that's negative 4 plus or minus b squared 16 minus 4 times a times c divided by 2 times a. 16 minus 32 is negative 16. Square root of negative 16 is 4i. Negative 2 plus or minus 2i. So y of t is going to be e to the negative 2t times c1 cosine 2t plus c2 sine 2t. Y of 0 is 3, tells us that c1 plus c2 equals 3. Or no, it doesn't. Y of 0 is c1 plus sine of 0 is 0. Tells us that c1 is 3. Y prime of t is negative 2e to the negative 2t times c1 cosine 2t plus c2 sine 2t plus e to the negative 2t negative 2c1 sine 2t plus 2c2 cosine 2t. Y prime of 0 equals 4 tells us that negative 2c1 plus 2c2 equals 4. C1 is 3, that's negative 6. Add 6 to both sides, that's 10. C2 is 5. C1 is 3. C2 is 5. Okay, you will have some of these higher order ones on the final as well. Here are characteristic equations of third order. When there's 4 terms like this, try to factor it by grouping. And in this case, the factor by grouping doesn't work. All right, so if that's the case, then you try to plug in numbers like 1. 1 minus 3 is negative 2 plus 3 is 1 minus 1 is 0. So 1 is a 0 of this. So we've pulled out using synthetic division. And so the remaining factor is r squared minus 2r plus 1. Well, r minus 1, and then r squared minus 2r plus 1 is r minus 1 and r minus 1. So it gives us r equals 1 with multiplicity 3. All right, so that's where we said that if you have these repeated roots like this, you'll get your traditional e to the rt, or r1 is 1t. But then to make the next solution linearly independent, you had to do a bump it up by a factor of t. And we have 3 of these, and then we have to bump it up again by a factor of t. And so there's our general solution. This one, our characteristic equations, r cubed minus 8 equals 0. And you guys have been hit with this one quite a bit in this class now. This was that one in class where I drew the picture. R equals 2 as one of them, and the other ones are up there on the complex plane. So it has a 60-degree angle there, and it's got a size of 2. So we know the cosine of 60 is negative 1/2, and the sine of 60 is root 3 over 2. And then this is negative 1/2 minus root 3 over 2. That's one way to figure it out. And the other way is to factor this r minus 2, r squared plus 2r plus 4. So we get one of them as r equals 2. And then the solutions to this one are going to be these guys, negative 1/2 plus or minus I root 3 over 2. And you can see that by saying r2 and 3 equals negative b plus or minus the square root of b squared minus 4 times 1 times 4 is minus 16 over 2. Negative 2 plus or minus square root of negative 12 over 2. Negative 2 plus or minus 2i root 3 over 2. So those are negative 1 plus or minus I root 3. So our general solution then is C1 e to the R1t. And then when we have complex numbers, the negative 1 is the e to the negative 1t. And then we get a C1 cosine root 3t plus C2 sine root 3t. Okay, so here was our other existence uniqueness theorem with the second order linear differential equations. It was just like the first one where it's the largest interval, so a one-dimensional number line. So we always would solve for y double prime by itself minus the t's divide out there. We have 1 over t plus 3 y prime plus t squared minus 9 over t plus 3. That's t minus 3t plus 3, so we'll have t minus 3 over t for that one. Y equals the natural log of t minus 4 over t minus 3, t and t plus 3. Okay, so our initial condition has a 1 in it. And so we want the largest interval on which the given initial value problem has unique solution. So we're looking for the largest interval containing 1 where all of these are continuous. So we have discontinuities for t equal to negative 3, t equals positive 3, and t equals 0. Sorry, I don't know why I said positive 3, because that's in the numerator. So we have negative 3 and 0. But then ln of absolute value t minus 4 says t can't be 4. All right, so our number line. The number in question is 1. We have discontinuity at negative 3, 0, and 4. And our point x not equal to 1 sits right between 0 and 4. So the largest interval containing x not equal to 1 in which the coefficients are continuous, is from 0 to 4. Largest interval is 0, 4. Okay. Largest interval containing x not equal to 0 where the coefficients are continuous is 0 to 4. All right, this one was pretty easy. Verify that y1 equals t squared and y2 equals t to the negative 1 are solutions. So this is just like what we did on the last test, but for those matrix systems. So y1 is t squared, so y1 prime is 2t and y1 double prime is 2. So if I plug it into t squared y double prime, that's t squared times 2 minus 2 times 2t, minus 2 times y, which is t squared. That's pretty easy to see that that's equal to 0. y2 prime is negative 1 over t squared, and y2 double prime is 2 over t cubed. When we plug that in, t squared times y double prime minus 2 times 1 over t, that is also clearly 0. Therefore, y1 and y2 are solutions to the DE. Now, since they're both solutions, we want to show that they're linearly independent, and then we can say that the general solution is any linear combination of those. So the Wronskian was our fancy way to show that functions are linearly independent and vector functions are linearly independent. The Wronskian of t squared and t to the negative 1 is the determinant of t squared 2t, t to the negative 1, negative t to the negative 2. So that's going to give us negative 1 minus 2, which is negative 3, and that is not equal to 0. Remember, the Wronskian, if they're solutions to a DE, they'll either always be non-zero or be 0. And so therefore, non-zero Wronskian implies that t squared and t to the negative 1 are linearly independent. General solution is easy now. We just know that any linear combination of these two functions, t squared and t to the negative 1, is the general solution. All right, method of undetermined coefficients, very important. The basis of method of undetermined coefficients is pretty simple. But remember, in order to do method of undetermined coefficients, we have to always make sure that the particular solution form of it is not a solution of the homogeneous. So we need the homogeneous first. Find the general solution. we have characteristic equation r squared minus 2r minus 8, which is r minus 4 and r plus 2. So we get r equals 4 and r equals negative 2. So the general solution then is c1e to the 4t plus c2e to the negative 2t. All right. As long as the right-hand side doesn't have an e to the 4t or e to the negative 2t, everything is fine. So to find a particular solution, we say that if the right side is a linear polynomial, then what we do is we try something of that same exact form, a t term and a constant term. Yp prime is a, yp double prime is 0. Plugging that into y double prime minus 2y prime minus 8y equals negative 32t plus 40. We have 0 minus 2a minus 8 times a t plus b. All right, so that's negative 8at plus negative 2a plus b. We can see then that negative 2a plus b is 40 and negative 8a is negative 32. A is 4. If a is 4, I think I have a mistake here somewhere. Sure do. That's negative 8at minus 2a minus 8b. All right, so that says that negative 8b equals 48, or b is negative 6. So yp is 4t minus 6. Okay, letter C. The form of the non-particular, the non-homogeneous side is a multiple of e to the negative t. So we would normally try something that is a multiple of that same piece. But what happens is when we plug it in, because e to the negative 2t is already a solution to the homogeneous, we're going to get 0 when we plug that in. So we'll see an error as soon as we do that. So what we have to do is bump it up by 1 dimension in this case, because the negative 2 was only multiplicity 1. So we have to append that factor of t on there. And so now yp prime is a e to the negative 2t minus 2a t e to the negative 2t. Yp double prime is negative 2a e to the negative 2t minus 2a e to the negative 2t plus 4a t e to the negative 2t. So that gives us negative 4a e to the negative 2t plus 4a t e to the negative 2t. All right, plugging all that stuff in there. Yp double prime minus 2y prime minus 8y equals negative 24 e to the negative 2t. Minus 8y is minus 8a t e to the negative 2t minus 2y prime is minus 2a e to the negative 2t plus 4a t e to the negative 2t, and then yp double prime is negative 4a to e to the negative 2t plus 4a t e to the negative 2t. Okay, so what happens here? We've got 4at plus 4at is 8, minus 8 is 0. And then we have negative 4 minus 2 is negative 6a e to the negative 2t equals negative 24 e to the negative 2t. So that says that a is equal to 4. All right, after all that, we get yp as 4a. I found out that a is 4. 4t e to the negative 2t. Okay, now we see that from B, y particular 1 was 4t minus 5. Sorry, let me hold on a second here. Okay, yp1 on this one is 4t minus 5. From B, what we had is negative 32t plus 40, which is negative 1/8 of that. So this right side of this is negative 1/8 of the right side from B. So therefore, our new yp is going to be negative 1/8 times the solution we found in B, 4t minus 6. And the y particular 1, or sorry, 2 is 72 e to the negative 2t. From C, we have negative 3 times negative 24 e to the negative 2t is 72 e to the negative 2t. So we use that same constant, negative 3 times the solution 4t e to the negative 2t, which gives us negative 1/2 t plus 3/4 minus 12t e to the negative 2t. So now our general solution is the homogeneous plus the particular. All right, this is definitely on the final. I gave you something a lot easier than that, though. Okay, so these were important. Use the method of Go ahead.
For the above problem, the part D, isn't it supposed to be the which one called? Isn't it supposed to be yp equal would be negative 1/8 over 4t minus 5 on part D, where you have the yp equals
No. You take this negative 1/8. This is
right.
the 4t minus 5. So you take negative 1/8 of the solution.
No. I mean, no. I understand that. It's just whatchamacallit. And the third row where you put the yp, where I'm looking at the yp, it says 4t minus 6. Isn't that one supposed to be the minus 5?
No, because that's what I mean. You're supposed to take negative 1/8. Once we found out that negative 1/8 of the non-homogeneous portion from B came out to the non-homogeneous portion in D, then that's the coefficient you use, and you multiply it by that solution.
You multiply it. Wait, what was the thing on that?
Times 4t minus 6.
Okay. Okay, yeah. Thank you. Sorry about that.
Oh, no problem. Okay, using the method of undetermined coefficients, determine the form of the particular solution. So just the form of it. And when we look at this, we have to know what the homogeneous solutions are before we get started in all these problems. So r squared plus 3r plus 2, r plus 2, r plus 1. So we got negative 2t plus c2e the negative t. And since the right side doesn't have any of those pieces, then we're just good with going forward with our particular solution. So if you have a 3t cubed, you must have a cubic polynomial. If you have a t e to the 14t, then you're going to have a linear in front of the e to the 14t. That's way too many unknowns to solve, so we're just asking for the form of it. Letter B, our characteristic equations r squared plus 25, which gives us r1 and 2 plus or minus 5i. The homogeneous solution of this would be a c1 cosine 5t and a c2 sine of 5t. But look at that, we got those pieces there. All right, so this is where a lot of people messed up on the test. Normally, our particular solution would be if you have cosine 5t or a sine 5t and or a sine 5t, you pick the highest of those orders. So if it's a t squared, then we have to have a quadratic or a squared, a degree 2 polynomial in front of cosine, but we also have to have the same degree in front of the sine 5t. Okay, but what we recognize here, though, is that one of these pieces, the b0 sine 5t, is a solution homogeneous, so we have to bump this up by a t. And then we have this t e to the t, which has no issues because it doesn't present itself in the homogeneous, but it is a first degree polynomial, so we'll do a c1t plus c0 e to the t. And then this one, we have characteristic equation r squared minus 6r minus 9. R equals 3 multiplicity 2. And again, remember that these plus or minus 5 i's, they reach multiplicity 1, which is why we put a t to the first. When you have multiplicity 2, you have to bump it up by t squared. So you have a t to the fourth e to the 3t. Our homogeneous solution is c1 e to the 3t plus c2 t e to the 3t. And our particular solution, we would normally try something of that same form, which is an a4 t to the fourth plus a3 t cubed plus a2 t squared plus a0 e to the 3t. But because it's multiplicity 2, we have to bump this up by a t squared. I missed the a1t, didn't I? Because this time these two are solutions to the homogeneous, so giving it a t squared makes those both not be present anymore. Okay, so that's method of undetermined coefficients. Method of variation of parameters. If we knew two solutions to the homogeneous, linearly independent solutions homogeneous, then our particular solution we found by varying the parameters. We took a v1 times y1 and a v2 times a y2. Now we took first derivatives of those, which gave us our first restriction. We wanted v1 prime y1 plus v2 prime y2 to be 0. We wanted those first derivatives to go away. And then the second one, when we plugged it in, we got v1 prime y1 prime plus v2 prime y2 prime equals t e to the t. That gave us a system of equations. So we have v1 prime times y1 plus v2 prime times y2 equals 0. v1 prime y1 prime plus v2 prime y2 prime. We use Kramer's rule to solve for the v1 and v1 prime. So this is the determinant divided by determinant. The denominator is the determinant of coefficients. The numerator is determinant. If it's v1, we replace the first column with the non-homogeneous portion. Taking those determinants, we have a minus t e to the 2t divided by e to the t plus t e to the t minus e to the t. These cancel, and so we're left with negative e to the t. v1 prime equals negative e to the t, or v1 is negative e to the t. We didn't put a constant of integration on those. There wasn't a need for those. And v2 prime then is 1 plus t1. This replaced with 0 t e to the t. Same determinant down here. It's the Wronskian. That was why we had to have them be linearly independent. We want the Wronskian to be non-zero. We have the same t e to the t. This is t e to the t plus t squared e to the t, which gives us 1 plus t. All right, when it asks for just the particular solution, y particular is v1 y1 plus v2 y2. V1 is negative e to the t times y1, which is 1 plus t. V2 is e to the t times y2. Sorry. V2 is t plus t squared over 2 times y2, which is e to the t. It's negative e to the t minus t e to the t plus t e to the t plus t squared over 2 e to the t. Cancels, cancels. We're left with negative e to the t plus t squared over 2 e to the t. All right, a 4-kilogram mass is attached to a horizontal spring with stiffness 16 Newton per meter. The spring is stretched so that it is displaced 4 meters to the right and given an initial velocity of 8 meters per second to the right. Neglecting any damping, find the equation of motion of the mass. And so our equation was my double prime plus by prime plus ky equals any external force. In this case, we're not driving it with anything. And so we have 4y double prime plus 16y equals 0. Or y double prime plus 4y equals 0 with a characteristic equation of r squared plus 4 equals 0, which gives us plus or minus 2i. Remember, this is simple harmonic motion stuff. Sums of sines and cosines. So y of t is c1 cosine 2t plus c2 sine 2t. If y of 0 equals 4, then that says c1 equals 4. Y prime of 0 equals 8 says 2c2 equals 8. c2 equals 4. So y of t is 4 cosine 2t plus 4 sine of 2t. So now writing this in the specified form, a sine omega t plus phi, we get y of t is the square root of the sum of those squares times sine of the same omega, and where tan phi is 4 over 4, which is 1. So that says phi, if they're both positive, then that says phi is inverse tangent of 1, which is pi over 4. And so therefore we have y of t is the square root of 32, which is 16 times 2, or 4 root 2 sine of 2t plus pi over 4. We want to know when it passes through equilibrium. When y of t is 0. So 0 equals 4 square root 2, sine of 2t plus pi over 4. 4 root 2 doesn't make this 0, so it just says 0 must be sine of 2t plus pi over 4. But we know that sine is 0 at all of its multiples of pi. 0, 1 pi, 2 pi. Equals all of our multiples of pi. And so then that says that, 2t, yeah, that was. Subtracting pi over 4 from both sides, it says that t is 2k pi minus pi over 2. All right, so that's going to be the first k that makes that positive, and that will be if k is 0. No, if k equals 0, then that's going to be negative. All right, I see I also made a mistake here. It should be 8 there. If I do k equals 0, it'll be negative, but k equal to, made 2 mistakes there. If I set k equal to 1, then this will be positive, and we'll have 3 pi over 8. A 1/2 kilogram mass is attached to a spring whose stiffness is 8 Newton meter. Damping constant B is 5 Newton second per meter. The mass is moved 3 meters to the right of equilibrium. And given initial velocity of 36 to the left. We have the equation of motion as my double prime plus by prime plus ky equals f external. M is 1/2, b is 5, k is 8. We have not given it any external force. Multiplying both sides by 2. We go characteristic equation, r squared plus 10r plus 16 equals 0. And that's r plus 8 and r plus 2 equals 0. When you get the two r's like that, this is either critically damped or overdamped. And so we have r equals -8 and r equals -2. So we have the equation of motion is c1 e to the -8t plus c2 e to the -2t. If y of 0 is 3, then we have c1 plus c2 equals 3. If y prime of 0 is -36, then we have -8c1 minus 2c2 is -36. This will give you c1 equals 5 and c2 is -2. So we have y of t equals 5e to the negative 8t minus 2e to the negative 2t. Does this system oscillate? No, because it doesn't have sines and or cosines. The system that we're working with now is overdamped. There's too much damping on this. And so remember the pictures on these kinds of things, if we pulled it out to 3 meters to the right of equilibrium, and then given a push to the left meant I tried to give it enough energy to cross equilibrium and then come right back down. But if you don't give it enough, I mean, that's why I said we'll drive it at 36 meters per second to the left. So you got this mass sitting on a table, and I pulled it out to here, but I pushed it hard back there so that it would cross through equilibrium. Both critical and overdamped can cross through its equilibrium. And you know that just by solving the equation. So it's going to cross through equilibrium if y equals 0. 0 equals 5e to the negative 8t minus 2e to the negative 2t. If we get a solution to this, or positive solution to this, then it does pass through its equilibrium. And so if we add 2e to the negative 2t to both sides, then we have 2e to the 6t equals 5, or e to the 6t equals 5 halves. That's what tells me right there that I have a solution. 5 halves isn't negative, and so we take the natural log of both sides and then divide by 6. So at 1/6 of natural log of 5 halves seconds, this mass will pass through its equilibrium. All right, the last one was about the about resonance, resonant frequency, and steady state solution. So we have a mass of 4 kilograms. Spring stiffness of 40. Viscous fluid so that the damping constant is 2 newtons second per meter. We did not drive the, we did not move the mass at all or give it any initial velocity, but instead what we did was drive it with an external force of 6 cosine 3t. And so when we did these, I asked for the steady state. And when you, this is an underdamped system. And you could see that's by setting up your differential equation and looking at the characteristic equation. So the steady state solution is the only thing that hangs around after some time, because the homogeneous is going to get, all the energy is going to be taken away from the damping. And that solution, y particular that we derived, is f naught over square root of k minus m gamma squared plus b squared gamma squared times sine of gamma t plus phi. the phi there is such that tan phi is equal to k minus m gamma squared over b gamma. So it's these pieces that I need to know what is going on. So I need to know what k minus m gamma is, and I need to know what b gamma is. K minus m gamma is 40 minus 4 times gamma, and this is our gamma right here. So we drive it with an external force of F naught cosine gamma t. So F naught is 6 and gamma is 3. All right, minus m gamma squared, which is 3 squared, 36, so that's 4. B gamma is 6. And so tan phi is 4/6 or 2/3. When it's positive, you can say that phi equals inverse tangent of 2/3. I don't know what that is that time, though. All right, F naught is 6. K minus m gamma squared we found to be 4. B gamma is 6. That's 16 plus 36, 52. (52) is 4 times 13. So we have 6 over 2 rad 13, which is 3 over rad 13. Sine of 3t plus phi. And where phi is the inverse tangent of 2/3. Okay, so now remember, it was all about varying the frequency of the driving force. It's all about varying gamma to obtain the maximum amplitude. The maximum amplitude is sitting right here. We want to vary gamma so that we get the max amplitude. So what we did was we took the derivative of that with respect to gamma and figured out what gamma maximized that. And what we ended up with was a gamma resonant. We came up with the square root of k over m minus b squared over 2m squared. And so remember, if you have simple harmonic motion, my double prime plus ky, the resonant frequency there was square root k over m. And so if b equals 0, meaning no damping, you get the same resonant frequency, square root k over m. So that was what we said. If you drove this at cosine square root k over m t, then we would hit resonance. The particular solution would have a t in front of the cosine square root k over m t. Where this one, though, is practical resonance, because when you have damping, you just get max amplitudes. So this is how they FM radio tunes into certain stations. So we plug all that stuff in there, and we have the square root of 40 over 4 minus 2 squared over 2 times 4 squared equals square root of 10 minus 1/8, which is a square root of 79/8, which is square root of 158 over 4. And so the resonant frequency is gamma r over 2 pi. All right. Exam 3. Okay, I know I went over some of this exam in class. I know I did this one in class. This is not on the final. I know I went over this one in class. And this is on the final. This is the same problem, just different numbers. Did I go over this one in class? Anyone remember? Thank you, Mason. I don't remember going over this one in class. Did I go over this one? Thank you, Mason. Okay, so seeking a power series solution about the point x not equal to 0. We know that our y of x is sigma n equal to 0 to infinity of a sub n x to the n. Y prime is n a n x to the n minus 1, n equals 1 to infinity. Y double prime is sigma n equal 2 to infinity of n minus 1 a sub n x to the n minus 2. We plug that back in here and we'll have one of our y double primes. And then we'll have minus x squared times that. So that will be from 0 to infinity, 2 to infinity. X squared times that is x to the n. Plus xy prime is going to be sigma n a n x to the n equals 1 to infinity plus 2 a n x to the n equals 0 to infinity equals 0. Okay, so we shift our indices. Add 2, add 2, add 2, add 2. Subtract 2. That one's ready to go because we want everything to be of the same power. That one's ready to go. And that one is ready to go as well. All right. So we release the first two terms. N equals 0 is 2 times 1. A2, x to the 0. That's 2, 1, and 0, plus 2a0. N equal to 1, that's 3 times 2 is 6, a3, x, plus a1x, plus 2 A1x. Now we have sigma n equals 0 to infinity of n plus 2, n plus 1, a sub n plus 2, minus n minus 1, a sub n, plus n, a sub n, plus 2, a sub n, x to the n equals 0. So there's our recurrence relation right there. N plus 2, n plus 1, a sub n plus 2. Those are all a sub n, so I'm going to bring them to the other side as positive n times n minus 1 a sub n minus n. Let's go ahead and factor out the a sub n as well. Minus n minus 2 a sub n. That's n squared minus 2n minus 2. And then I divide by n plus 2, n plus 1. There's our recurrence relation. Now, from this piece here, 2a2 plus a1, that's got to be equal to 0. From this one right here, that says that 6a3 plus 3a1 must be 0. And so that says, the first one says that a2 is negative 1/2 of a0. And this one says that a3 is negative 1/2 of a1. Yeah, I wrote that down incorrectly, didn't I? It's 2a0, so that says that a2 is negative a0. But it says that a3 is negative 1/2 a1. Find the first 6 non-zero terms in the power series expansion. Okay, so we have a0 already. We have a1. We have a2, which is negative a0. We have a3, which is negative 1/2 a1. And now a4 is when n equals 2, so that's 2 squared is 4, minus 4 is 0, minus 2, over 2 plus 2 is 4, times 2 plus 1, that's 3, that's 12. A2, or negative 1/6 times A2, which is negative A0, 1/6 of A0. A5 is when n equals 3, so that's 3 squared is 9, minus 6 is 3, minus 2 is 1, over 3 plus 2 is 6, 3 plus 2 is 5, times 3 plus 1 is 4 is 20. Times A3, so that's 1/20th times negative 1/2 A1, which is negative 1/40th A1. I think that's the first 6 non-zero terms, but I took it one step further just to be safe. A6 turned out to be 6/30ths times A4, which is 1/5 times A4, which is 1/6 A0, which gave us 1/30th of A0. Okay, so remember the two-step recurrence relations mean we're going to have two different forms for this. We're going to have the A naught plus A2x squared plus A4x to the fourth plus A6x to the sixth. And then we're going to have A1x plus A3x cubed plus A5x to the fifth. And so then the first piece, the A0 is going to factor out, and we'll have a 1. A2 is negative A0. A4 is 1/6. and A6 is 1/30. A1, that'll be an x plus A3, which is negative 1/2. A5 is negative 1/40. And that's our final solution for the specified number of terms. Minimum value for the radius of convergence of the power series solution that has the following form. So your point that you're expanding about is 5, and you wanted the distance from 5 to the nearest singularity of this equation. And the singularities are negative 3. We did x cubed minus 8. X cubed plus 27 is negative 3, and then you have those two solutions right there. X plus 3, x squared minus 3x plus 9. Throw those into the quadratic formula, and you get 3/2 plus or minus 3 root 3 over 3i. So we're looking at a negative 3. We're looking at 3/2 plus root 3 over 3i and 3/2 minus root 3 over 3i, and 5 sits out here. So the smallest distance is going to be the distance to those 2 points, which turns out to be root 19. So the minimum radius convergence is root 19. You will be asked to solve a Cauchy-Euler equation. And so remember the characteristic equation for these: r times r minus 1 minus 5r plus 9. R squared minus r minus 5r is minus 6r plus 9. And we get multiplicity 2 there, r equals 3. So we go C1 x to the third. So these were always solutions of the form x to the r. But if they weren't distinct, then we had to take the x to the third and multiply by a natural log of x. Now this would be the solution if we said for x greater than 0. If it's x not equal to 0, then we have to put the absolute values on those. Letter B, you make a change of variables and then put it back in the end to realize that instead of x's, it's just going to be x minus 1s. So we have the same kind of characteristic equation. R times r minus 1 is r squared minus r plus 3r plus 10 equals 0. This gives us imaginary solutions, negative 2. Did I do something wrong here? Yeah, 3r minus r is 2r. Negative 2 plus or minus the square root of b squared minus 4ac divided by 2a. That's negative 2 plus or minus 4 minus 40 is the square root of negative 36. And so that's negative 1 plus or minus 3i. So we get a C1 x minus 1 to the negative 1, but absolute values on those because x doesn't equal 1. If it was greater than 1, we would just use x minus 1 to the first. Times a cosine of 3 natural log of x minus 1 plus C2 absolute value of x minus 1 to the negative 1 sine of 3 times absolute natural log of x minus 1. Okay, save you guys a little bit of time in studying. There's going to be no singular, no regular singular or irregular singular points on the test, and I won't ask you anything about Frobenius method. All right, exam 4. You guys did pretty well on this test. The definition of Laplace transform. When I say use the definition, we have to plug it in here. So if we want to know what the Laplace transform of cosine bt is, we have the integral from 0 to negative infinity of e to the negative st. That's f of t. So I'll pull the 1/2 out in front of that, and I have e to the bt plus e to the negative bt dt. So that integral is 1/2 times the limit as n approaches infinity of 0 to n of e to the negative s minus bt dt plus 0 to n of e to the negative s plus b t dt. That's 1/2 the limit as n approaches infinity. That integral is going to be 1 over negative s minus b e to the negative s minus b t evaluated from 0 to n. This one's going to be 1/2 limit as n approaches infinity of 1 over negative s plus b e to the opposite of s plus b t evaluated from 0 to n. This is 1 over negative s minus b times e to the negative s minus bn minus e to the 0, which is 1. Plus 1/2 limit as n approaches infinity of 1 over the opposite of s plus b e to the opposite s plus b to the n minus 1. Now this is equal to 1/2 times 1 over s minus b plus 1/2 1 over s plus b if s is greater than b. If s is greater than b, then that's a positive number, and then that goes to 0. If s is greater than b, then s plus b is a positive number, and that goes to 0. So a lot of you guys forgot to write that step. So that's actually fine to leave it like that. You've showed me what the Laplace transform is, or you get a common denominator, s plus b, s minus b over 2 times s minus b, s plus b. This gives us s over s squared minus b squared. Find the Laplace transforms of these. Laplace transform of 3t to the 7th is 3 times 7 factorial over s to the 8th. When you take the Laplace transform of something times t, or sorry, e to the negative 2t times t, bring out the minus 5. Laplace transform of t is 1 over s squared, but the Laplace transform of e to the negative 2t times t translates it by a negative 2 or a plus 2, s plus 2 squared. So this is 5 over s plus 2 squared. Laplace transform e to the 9t sine 5t. This is equal to f of s minus 9, where f of s is the Laplace transform of sine 5t. Laplace transform of sine 5t is 5 over s squared plus 25. So we have 5 over s minus 9 squared plus 25. Number 5, the way I worked with this one is I know that the Laplace transform of a t times some kind of f of t is negative 1 times d ds of the Laplace transform of f of t. So we have there is a negative 1 times d ds of the Laplace transform of e to the negative 2t sine 3t. So that's 3 over s plus 2 squared plus 9, derivative of that. And the derivative of that is the denominator is the negative 1 power, so I bring a negative up. And subtract 1 from it, which makes it a 2. We take the derivative of the stuff inside, which is 2 times s plus 2. And so that gives us positive 6 times s plus 2 divided by s plus 2 squared plus 9 squared. Okay, I'm running out of time here. I've got my next class that I have to meet them online as well. But I will finish this and post the recorded video on YouTube, and I'll send you guys the link. I probably will not be able to get to it till tomorrow. So I'll send you guys an email when that thing's ready for you guys to view, but you guys deserve the rest of these solutions. So I do have time for any questions if you have them, though.
Question, yeah. Are you going to give us are you going to allow us to use a note card for the Laplace transform?
I'll let you guys use it. I'll let you use a sheet of paper. I don't really care. Use
a whole sheet of paper?
Whole sheet of paper.
One side or two side?
3-sided.
3-sided? Okay. Got it.
You can whatever you want. One sheet of paper, 2-sided. I should be careful how I say that, huh? People are going to show up with 3-sided papers.
Yeah. All right. Thank you.
You're welcome. Any other questions? Okay, I'm going to go ahead and adjourn, and I will let you guys know when I have the remaining. Those are definitely fair game, Mason. Those, yeah, you need to know how to do those. Yep. Any other questions, class? Oh, you're welcome, Mason. I just learned how to use this. This software is called Zoom, and it's pretty cool. It's how I teach all my online classes. feel sorry for faculty who don't know how to use this kind of stuff. So if their class gets canceled, there's nothing they can do.
Wait, so is Zoom like something that you basically screen share onto the thing? Or you screen?
Yeah, I mean, I can. I hate doing this because I'm not really. I can also use video, as you could probably. Can you guys see me now?
Yeah.
Yeah, I can use video, all that stuff. So it's actually quite cool. So I can screen share. I can share any application I want. There's also ways to like allow you guys to take over and write on the board and put you in rooms to write together and that kind of thing. So it is pretty cool, and I think it's free. I'm thinking, I don't know if it's free actually. I know it's free for me because of the California Community College thing. But anyway, any other quick questions while you guys have me? All right, I'm really glad that you guys showed up. And like I said, study these exams. Do them backward and forward. Make sure you know all these exams. The problems on the final will be much easier than the problems on these exams. So you will be fine on this final if you can reproduce these exams. Now, I do need to preface this. I do not want, I'm going to look at you guys' note sheets before you guys take this test. I do not want to see the problems from my exams written on there in hopes of me giving you something like that. I just want you to have this note sheet so you can write down formulas, and I don't want you to have to write super small and that kind of thing. It's basically to take out the memorization portion of it. You can write down procedures and formulas. I just don't want to see a bunch of problems written down.
Got it. Thank you.
All right. Okay, everybody, I will send you out a link when I have the rest of this video recorded. And I'll see you guys on Thursday.